Okay, thank you. Hi. This is work done primarily by Alexandros, who was a student at the University of Crete and who sadly could not be here today because he just started his PhD and had to move to the US. Also work done together with Iacovos, Foivos from Red Hat, and Angelos, Bilas, and me, who are both faculty at the University of Crete. So, what's the problem here? We are trying to find data races in Java parallel programs. And data races are difficult to find, and there are many tools that try to find races, both statically and dynamically. And these, the problem and the issue with the existing tools at this point is that many or most have a problem in terms of practicality and how to deploy in a production setting. Things that can go wrong are, for static tools that try to usually be sound, are the false positive generation. So for every data race, you have to analyze hundreds and sometimes even thousands of warnings, right? Also, static tools have the drawback that you need the whole program to analyze, and the analysis of big production-grade codes might involve hundreds of thousands or millions of lines, and static analysis might not scale. But one other thing we found that is a problem for both static tools and dynamic tools that do instrumentation statically is that many of these production codes generate and then load Java bytecode on the fly. So you have code that produces Java bytecode and then loads it and runs it, and this is very difficult to either analyze statically or annotate statically. The other thing that's a problem with dynamic tools is performance, because most of these dynamic tools usually run Java in the interpreted mode, and that is all well if you're running small programs, but if you want to run either a big program or your program with a huge data set and a long execution, then running in interpreted mode is not very practical. The other final issue that you might have is that the current state of the art is usually some sort of algorithm or analysis or tool that's been ported to Java from a different language. The main competitor here is the thread sanitizer, right? And there are issues with the Java memory model and the Java concurrency spec that you might not get. So the objective of this work is we want to build a dynamic race detector, and we want to build it specifically for Java, and we want it to be very practical. So we want to be inside the OpenJDK, and by inside the OpenJDK, I mean we want it to be very fast, so we need full JIT support, make hotspot work. We want to work with garbage collection, and hopefully with all garbage collectors that you get in the JVM. And we want to handle the semantics correctly for the Java memory model, the JMM. And that hopefully will give you less false negatives, so you don't miss any races, and you get better support for things that will go in reality. The other goal was to generate output that is very, very useful for debugging. So you cannot just point at this memory location. You get 0x, FFFF, ABCD, and that's your race warning. That's not very helpful if you're a Java developer, right? So you want to translate things back into source lines and stack traces. Okay. And we want to run real stuff, large applications, large data sets, large codes. So what we did is we built this tool called MaTSa, and here the name is the closest we could get to paying tribute to the thread sanitizer TSan, and TSan if you spell it a different way, is a kind of herbal tea, right? So again, if you pronounce this wrong, it's matcha, which is another kind of tea, except ours is with caffeine, so it goes faster. And the idea is we implement the fast-track algorithm like the thread sanitizer, the same idea with vector clocks, a bit differently so that we capture the Java nuance. We integrate this into OpenJDK. We support JIT, all the JIT compilers in the JDK. We track all kinds of memory accesses that matter and can produce races. And so this counts a lot for performance, because the Java memory model helps you get rid of some things that you would have to instrument otherwise. And we have a novel technique for producing better race warnings, so we can reconstruct the stack when something goes wrong. We compare against the thread sanitizer, the current state of the art, and we do an experimental evaluation on a set of small benchmarks so that we can compare, and then sets of benchmarks that at this point no other tool can run. We found races, we found unknown races, and some of them have been fixed in the repositories upstream. And so I'm going to give you a small summary of how this algorithm works. This is not our idea, this is the algorithm used also by thread sanitizer, right? So we want to detect what happens before what, and by extension, what could happen in parallel, and thus is a race. Let's say you have two threads, and we give every thread a vector clock. And here, every thread has a vector clock where the first location is the clock that I know of. Let's say I'm thread 1. Thread 1 is at clock 0, and thread 1 knows that thread 2 is also at clock 0. And then thread 2 has a similar vector clock. Its own time is 0, and it knows about thread 1 that is also 0. Right? So every thread has a vector of clocks capturing what they know about the other threads. And then we put a vector clock also in every lock, and by extension, I'm going to extrapolate to every other synchronization mechanism that you might have. And then every time a thread does something of relevance, it advances its clock. Right? So thread 1 is now at clock 1, at time 1. And then maybe thread 2 advances its clock, right? And so every thread can observe some notion of time. But then when you lock and you acquire the lock, the clocks are synchronized. We're going to pull whatever the lock has captured from the other threads and put it in thread 1. In this example, there's nothing. But then when the other thread is going to try and get the lock, it's going to block and get the lock as soon as it's released by the first thread. On release, you get the time from thread 1 and you save it in the lock. So what the threads communicate to each other is basically, what do you know about where everyone else is? And this is done through the locks. So we take the vector from thread 1 and we save it. We add it to whatever is stored in the lock. This is the information. This lock now knows that thread 1 has advanced at least up to that point. And then when the lock gets locked by thread 2 is going to find that out. So now thread 2 knows via the lock that thread 1 has advanced at least up until time 1. Everything that's happened in thread 1 up until time 1, now thread 2 knows that it's happened. So we say that's everything that has happened in thread 1 up until that release has happened before everything that's going to happen in thread 2 from that acquire on. And so this gives us a way to detect this happens before relationship. Okay. And using this happens before relationship, we can figure out if two accesses can happen at the same time and then flag a race. So on every access, if we have this happens before relationship, what you need to do is log somewhere what thread did the access, which memory location, right? Was this a read or was it a write? What time? Stuff like this. And then with this information, every time there's a subsequent access, you can compare with the last accesses that you've logged and figure out, oh, there's somebody that has not happened before me, so it could happen in parallel. The clocks are not necessarily larger or necessarily smaller from each other, and thus these two accesses can race, and so you can flag a race warning. And so this is the algorithm, the fast track algorithm. This is what TSan uses as well. And so we are based on this. And here's where the differences start. We want a fast representation. So we also use shadow memory. You have the Java heap, so you map it on a very, very big chunk of memory that's going to store all these access logs. But then you don't have to map every memory location in the process. Because in Java, the only thing that can be racy are field accesses, basically. Nothing on the stack can be shared. The objects, the rest of the stuff in the objects are not updatable. So there's one difference there where you can save memory and change the representation of shadow memory of what accesses you're logging. We remember the 4 last accesses, which is similar to the state of the art. And the other thing we do that's different is every time we log an access, we have a specific mechanism to also capture the minimal information so that you're fast, the minimal information that you require to rebuild the stack trace for that access, because you might discover that this access is involved in a race 2 seconds later, and that stack is going to be gone. So you have to reconstruct the stack so that you can say, this access that just happens now races with that access that happened a while ago, maybe in the next execution that you run the program, and I can reconstruct and show you the programmer a stack trace for both so that you can track the code and fight the bug better. So this is another problem that we solve specifically in this work. How can you very, very fast log the information that you need so that you can reconstruct stack traces that are gone by now so that you can produce better warnings. Okay, design points for this tool. We use a shadow memory to store the access log, plus this new thing, the stack reconstruction logs. We want to work with a garbage collector inside the JVM, and the garbage collector might change object locations, so the same thing, x.o, that would be in address 0 when your program runs, after the garbage collection might have moved to address 5, right? So you want to keep track of which accesses refer to which locations. What the people do so far is when you migrate your object with a garbage collector, you go and find the trace for all the accesses in that object and migrate those as well. And that turns out is very expensive. And it turns out, and the details are in the paper of how we measured this, that it's actually not worth it, because if you just wipe everything from the logs part of the memory, and you, every time you garbage collect, and you unmap all the memory, so you free it, you return it to the operating system, you're not going to miss many warnings, right? The garbage collector does not fire that often, especially in this setup. Okay. The other thing with garbage collection is that you will change the location of objects, which means you will change the location of locks in memory. Because in Java, every object is also a lock. There are 2 lock interfaces in Java, and one is the object lock. This is the implementation of the synchronized blocks and synchronized methods. Our solution to this is we embed the vector clock inside the object header, so we had to change the object header and some of the internals to make it work in OpenJDK. And so that when you move objects, the lock follows and all the vector clocks work. And this works with every garbage collector inside the OpenJDK. The other thing is this idea where you have to reconstruct the stack. And reconstructing the stack is a kind of time travel. So we want to figure out, after you pop all the stack frames and you do something else, that I should have taken a photo of that stack. And that's what people did so far. They took a photo of the stack on every axis. And copying around all these photos is very, very expensive. So these tools used to be very slow. What we do is we have a buffer for every thread, the stack event buffer, and we just append to that buffer. So that's an immutable data structure. You start with a copy of the stack, and then every time you enter a method, you add the enter method event. Every time you exit the method, you don't pop it. You add an exit method event. Okay, so far it's just a trace. The good thing about this representation is you can restart at all times. It's very easy to restart. When your buffer is full, when you want to make some space, whatever, you just start a new buffer and you just copy the existing stack there, and then you never have to go back to the old buffer again. Okay. You can append there. So you can restart at every point very, very fast. And the other thing is, every time you log an access, all you need is a reference. I was at that index inside that buffer, and then you can walk backwards in the buffer and reconstruct the stack up to main. Okay, that's the idea. It's really a simple idea, but I don't know what nobody did it so far. So we do this, and it really, really reduces the time for managing and producing the information for the warnings. The other thing we did differently is we group all these warnings in terms of source lines. So if you have the same data race and you run this code 1,000,000 times, you don't get 1,000,000 warnings for 1,000,000 different objects. The programming can say, this is one data race that involves maybe 1,000,000 objects, but it's between this source line and that source line. Okay, so we implemented this in Hotspot in both the C1 and C2 just-in-time compilers in OpenJDK. We instrument the code in the intermediate representation for the Hotspot compilers. We instrument every read and every write that can raise. So this is not every read and every write in the whole process, right? And so this makes it faster too. Being able to JIT compile is also much faster than interpreter. Unfortunately, because you instrument almost every read and every write on a field, there are many optimizations happening in C1 and C2 that you cannot do anymore. You cannot reorder stuff very easily around. And so it's much faster than what you would get so far, but up to a point. This is not as fast as not running a race detector. Okay. The other things we do for speed is when we create this access cell, we need to check on every access the previous accesses to compare and see if there's a data race. And this, because this is a SIMD operation, basically, with some tweaking in the JIT compiler, we can take advantage of x86 vector operations and make this operation very, very fast. The final thing, the large amount of work you need to do here is instrument all custom synchronization operations. And so you have to go inside the library, Java util concurrent. This is custom locks, read-writer locks, and all that, and do the vector clock thing to find out the happens before edges. Okay, so to summarize all these differences between our tool and the state-of-the-art, we work with the full stack interpreter plus Hotspot JIT compiler. We ignore synchronization that happens in volatile fields, and I'm going to explain this in a bit, instead of modeling them as synchronization. We found some issues with the Java memory model and how you treat static initializers, and I think I'm going to try tell you very fast how this is more correct. And we have some differences in how we handle thread join. The thing with volatile fields is that people write code like this, where there's a while that's going to spin on a volatile field up until there's a thread that writes the volatile field and takes you out of the spin. And a lot of people write custom synchronization code like this, and the Java memory model allows you to synchronize like this, because the Java memory model says a write on a volatile field and a read from a volatile field will have a happens before, will synchronize everything else in memory, even another third place in memory that's not volatile. The problem is that you can write code without the while, and there is no dynamic analysis that can tell this is an implementation of a spin lock and that isn't. This is a race, right? And so, because people do this and it produces warnings, what dynamic tools do is basically ignore all of volatile and raise their hands up and say there's no race here, although there is. So this is the main one of the issues with Java nuance. You can find many more such issues in the paper. Okay, so we run this and we measure how fast it is, and it turns out that we are quite slower than running just the JDK, but quite faster than what people would do so far. Okay, if you can JIT compile, basically everything becomes faster. Okay, I'm a bit over. Okay, so I'm going to take a couple of minutes from the question time and to say that we also measure the memory usage, how much memory you use. And it turns out, these are gigabytes, it turns out you should be using at worst 4 times the memory than your Java heap. And this is very, very variable from application to application because of page locality, because you will always memory map 4 times your heap, but sometimes there are things in the heap that are never accessed, and so these pages are never going to materialize in the shadow heap. And the other thing here I'm going to explain is this thing. Sometimes we use less memory than even Java. In the end, we are 15 times faster than the competition. If you want to find races, we can run with heaps that are many gigabytes in size with big benchmarks. At this point, you cannot run anything with interpreter rolling tools like this. And sometimes we even use less memory, but that is a side effect because when we use less memory, because there's more memory pressure, and so we're going to call the garbage collector much more often. And in some applications, this just reduces the residence set in memory. So, what doesn't work? If you write custom synchronization with volatile fields, it doesn't work. If you use synchronization from other languages, so in some of these benchmarks, you would see 100 warnings. This is because these benchmarks are written in Scala, and Scala has its own in-lock implementations. And so you have to go into the library and say, you have to synchronize the vector clocks. We sometimes opt to create false positives just so we don't miss any real races. There is this trick. Most people think the object constructor is thread local because usually new is run by one single thread and then you share the object. But sometimes inside the constructor you can lick the this pointer and that might give you a race. So basically we're going to find races that are not there so that we don't miss that. I conclude here saying that I think this is the fastest at this point, dynamic race detection for Java. We can run bigger programs than anyone else. It's native to OpenJDK. It's much faster than because of JIT. It can be used for any language that produces Java bytecode, but it's going to take some porting to map the synchronization primitives to our system. Thank you.
Okay. Okay, thank you very much for the presentation. Yeah, we have questions. Yeah, if you want.
Support what? Volatile, yes. We do not consider them to be synchronization.
Yes.
Okay.
And I also assume that atomics would treat the same?
Yes.
Okay, I had two questions.
Because they do synchronize memory, but they do not enforce a happens before. They are not, they don't stop anybody.
So I had two questions. First, do you observe any false positive because of that?
Yes.
And second is why exactly you do not support them? Because I feel for example, Crete synthesizer supports atomics, and it can model what happens before atomics.
So the idea is, if you can use a volatile variable, like in this example, to implement a spin weight, right? And here, there's no race. You will actually make thread 1 wait until this right.
Yeah.
Okay. But there, it is a race, right? Because the access to y is not synchronized by it. And all the tools that consider volatile accesses to synchronize with each other will miss this race. So in order not to miss this race, we have to allow this false positive.
I mean, it depends where you read from dynamically. If you read from volatile, right? Yes, it would miss, but you can be lucky and you hit execution when it reads from different ways, and you will observe the risk.
So the whole problem is that here there's no mechanism to enforce ordering between the volatile access and the volatile access, right? And this is an illusion that there's an enforced ordering here. Because Java says this volatile access and that volatile read up there on X is going to synchronize memory. So the value of Y that you read after the while is definitely going to be the value of Y that you write here. Okay. If you don't have the while and you just use a volatile variable, what the other tools that try to model this will do is you have a volatile read here and a volatile write here. And they will assume that the volatile write and the volatile read synchronize. So you will miss that this access and the other access to Y can actually happen in parallel. Right? And this is a missed race. And this is why we consider more correct to allow the false positives so that you don't miss any. Because it is a happens before in terms of memory, but it's not an enforced ordering. Okay.
We can speak after.
Okay.
Further explain this example. Thank you.
As a small follow-up, so could you instrument this code somehow to detect traces here or to showcase the true behavior?
So could you, my answer would be no, because it would be akin to, can you verify automatically that this is a correct implementation of a spin lock?
Okay, but sorry, when I said instrument, I mean, could you actually use API into your own?
Yes, that's what we do.
Okay, and so this is how your instrumentation of the concurrent primitives works, I guess.
So the instrumentation itself is inside the interpreter and JIT compilers, but if you're using custom implementations, there's an API, you can do MaTSa.acquire, MaTSa.release, and then the system will know about it and treat it like a lock.
And sorry, for the last question, for all the concurrent primitives that you have, is there some sort of commonality between these concurrent primitives, and would it be like a lot of work to actually port this to, say, Kotlin versions of the same?
So the more flavors of a lock that you have, the more points you need to touch. That's the, yeah. So,
Thank you for the talk. You said that your instrumentation disables a lot of compiler optimizations.
Reorderings mostly, yes.
How much of the overhead of the tool do you think actually comes from the payload of the probe versus optimizations now actually off?
So there is some measurement in the paper about the difference between C1 and C2. Sorry. No. But it's basically, you lose most of the optimization that C2 would do over C1. So our performance with C1 and C2 is more or less the same. The benefit is much less than you would get in a vanilla OpenJDK.
Okay. And also, you said you instrument every read and write, which I'm imagining is going to cause there to be a lot of...
Every read and write that could race.
That could race. Is there any strategies where you don't have to instrument?
So, it would be really nice if we had a static analysis that could say, you know, all of these things are contained within a stack frame. Let's say you don't need to instrument them. But we don't at this point.
Thank you.
And the last question.
Thank you for the talk, and I think it's a great technical contribution. And my question is about the performance evaluation. So you mentioned that you are much faster than TSan, and compared to it, you do not support, you ignore volatile field accesses and atomic operations, while your competitor does not. So I wonder whether the performance benefits come from this ignorance or from something else.
It's from the interpreter versus JIT, clearly, yes. If we disable our JIT, so this is our system with just interpreter, right? And you can see, right, you go from 1 minute to 30 seconds just by enabling JIT. With TSan, it's comparable. Not always, but interpreter is interpreter.
Okay, I see.
Well, thank you again for the great talk. You can find Polyvios around